Okay, hi everyone. I'm presenting information-directed sampling and bandits with heteroscedastic noise. And that's joint work with Andreas Krause at ETH. My name is Johannes Kirschner. So we consider the usual stochastic bandit setting, where at time t the algorithm picks an action xt from an action set x, and then observes the reward yt given by some function evaluation at xt plus some noise epsilon t. And as usual, our goal is to minimize regret. Now, existing work assumes that this noise epsilon t can be bounded independent of the action chosen. And that we found to be restrictive in many applications. For example, right now we look into tuning the Swiss free electron laser together with our collaborators by using these bandit techniques. And there we observe that the noise distribution actually depends on the different parameter settings chosen. So in this work, we relax the noise assumption and allow the noise variance to depend on the action xt. So specifically, we are going to assume that at action x, the noise is rho x sub Gaussian. And for now, we're going to assume that this noise function rho of x is known. Okay, now in this setting of stochastic bandits with heteroscedastic noise, there are two key differences compared to the setting with homoscedastic noise. The first one is that we can make use of the noise bound to build a better estimator. For example, say the reward function is linear, and we are using a regularized least squares approach. We can add these weights in front of the residuals, kind of normalizing the data to get a more efficient estimator. This is known as weighted least squares and also works similarly in the kernelized setting. So this, of course, applies to many algorithms. For example, we can plug that in UCB and hope to get a more efficient algorithm. So what this story makes the point which makes the story interesting is that we can also use noise for exploration. So intuitively speaking, less noise should mean more information. So if there's correlations among the actions, we hope that we can exploit this correlation together with the knowledge on the noise for faster learning. And I'm going to show you next that two standard algorithms, UCB and Thompson Sampling, don't do that in a smart way. So in this example, we have four actions, x1 to x4. And we have a function class which has only two parameters, theta1 and theta2. So theta1 gives you the function value at the first two actions, x1 and x2, and theta1 gives the function value at x3 and x4. So in that case, we have two pairs of correlated actions. Now we're adding here heteroscedastic noise in a way such that the first action of each pair has low noise, and the second action of each pair has high noise. Now, given some samples, like shown in this picture, we can construct estimators for theta1 and theta2, and from these we get predictive intervals for all of the actions. But by exploiting the structure of this function class, the upper confidence bounds, for example, is going to be the same for the action x3 and x4. So the UCB algorithm, which picks the action which the largest upper confidence bound, has no natural preference between x3 and x4. Even though we now know in that example that x3 is the more informative action. And the same can be shown for Thompson sampling. So our contribution here is a new framework to analyze regret in the frequentist setting. And from that framework, we motivate a strategy called information-directed sampling, which resolves this kind of example. And then we apply this framework to the setting of heteroscedastic bandits. Now, from that example, we've learned that we need some notion of information gain to be able to prefer actions which are more informative, given that everything else is the same. So I'm introducing this abstract notion of information gain, a sequence of functions it, such that it of x gives you the expected information gain of playing action x at time t. And I'm keeping that abstract for now and showing you a more concrete choice later. But what I'm going to assume is that the total information gain, meaning the sum over the itxt, is bounded by some constant gamma t. And with that, we have the following theorem. So for any deterministic policy, we can always bound the regret by the sum over the square root, by the square root of the sum over the gap squared divided by the information gain times the total information gain. That proof is quite simple. So we write the regret as the sum over the gaps. Then we introduce the information gain. Then we apply Cauchy-Schwarz to separate the information gain from what remains. And then use our assumption that the total information gain is bounded. And that, if you're familiar with the proof of the UCB algorithm, then that's exactly the technique which is also used there. Okay, so the theorem kind of tells us that we want policies which have small information regret ratio. But we are not given this delta of x because it depends on the optimal action. But what we can do is, using confidence intervals, we can construct an upper estimate on the gap by taking the largest upper confidence bound on the domain minus the lower confidence bound at action x. Okay, so using that definition, we define deterministic information-directed sampling as the policy which, at time t, plays the action minimizing this estimated regret squared divided by the information gain. Okay, so that can be taken one step further. Instead of just optimizing this ratio over single actions, we can optimize this ratio over sampling distributions. Now, I can explain you details at the poster, but I just wanted to note that this ratio is always smaller than the one obtained by the deterministic version. Okay, and this is inspired to some extent by the Bayesian IDS framework by Russo and Van Roy from 2013. But we set it up in a frequentist framework, so our policy is not the same. And there are several technical challenges we address, and also we deal with continuous action sets. So here's a brief summary of our technical contributions. The theorem I just showed you also holds for randomized policies. So the regret of any randomized policy can be bounded with high probability like that, and compared to the previous version, we only lose a log 1 over delta factor for considering randomized policies. And this, of course, that theorem is what motivates the definition of information-directed sampling. Then we show that this minimization problem has the curious property that the solution can always be supported on at most 2 actions, which allows to compute this policy. Then we generalize known bound for online least squares regression to the heteroscedastic case, both in linear case and RHS setting. We introduce several information gain functions, which we use to define practical versions of IDS. And for some of them, we also bound frequentist regret bounds in the heteroscedastic stochastic bandit setting. Okay, so now it remains to choose this information gain function IT of x, because so far in the framework, nothing really depends on this on the heteroscedasticity. So one idea we had is that we can tailor the information gain function towards existing algorithms. So we use the UCB action to define the information gain function IT UCB as the reduction in the width of the confidence at the UCB action by playing action x. And of course, that's going to depend on the noise level at the action x. And if everything was set up in the Bayesian framework, then that is actually the mutual information between x and the value at the UCB action. Okay, and the resulting version we call IDS UCB. And the regret guarantee we prove is in the worst case the same as the worst case bound known for UCB. So we tried that in a simple experiment with a linear response function. So here you see the performance of the UCB algorithm, which ignores that there's heteroscedastic noise by just using a uniform upper bound. Okay, now we can of course use UCB with a weighted least squares estimator, as I said initially. And by using this more efficient estimator, we get an algorithm which performs better in that case. Now, IDS UCB is also using the same estimator as weighted UCB, but it also uses the noise bound for exploration. So in that case, we also improve on weighted UCB. So we explore several more information gain functions I can show you on the poster. Yeah, and I hope to see you there. Thank you.
Questions before Claudio?
No. No, we don't have instant dependent bounds. No, so this benefit is mainly there if there's correlations among the actions, and I think the only instant dependent bound known there is by Toa-Latimore and Java in the linear setting, and yeah, we haven't looked into translating that result to that setting, to instant dependent bounds. Yeah.
Okay, so before everybody leaves, let's thank all the speakers of the session and sorry for delaying the lunch.